Okay, so now I'm gonna watch this playlist here. The rest of the playlist. I'm gonna try to keep quiet because it's night here. People are sleeping, so don't wanna make too much noise.
The Einstein field equations, we're going to see how they predict the existence of black holes, gravitational waves, and the expansion of the universe. If you like, you can skip this video and cover these sections in any order, but for the Relativity 108 videos, we're going to cover black holes using the Schwarzschild metric. The Schwarzschild metric is the spacetime metric for a spherically symmetric, non-rotating mass that has no electric charge. It's useful for describing the curvature of spacetime near slowly rotating spherical bodies like planets and many stars. It's also useful for describing spacetime curvature near non-rotating black holes. The Schwarzschild metric predicts gravitational time dilation, the gravitational Doppler effect, the bending of light due to gravity, shifting in the perihelion of orbits, and the existence of black holes, with an event horizon with a radius of Rs, which is also called the Schwarzschild radius. The metric was first discovered by Carl Schwarzschild, who published it only a few months after Einstein's general relativity paper in 1915. Schwarzschild unfortunately died only a few months later while serving in the German army in World War I. In this video, 108a, we'll start by deriving the Schwarzschild metric from some starting assumptions. Then in 108b, we'll interpret what the metric means, explaining gravitational time dilation and also explaining a black hole's event horizon. In 108c, we'll calculate the geodesics of the Schwarzschild metric, which give the paths of light beams and massive bodies in the presence of gravity, which includes the perihelion shift of orbits. In 108d, we'll cover some alternative coordinate systems for the Schwarzschild geometry that make it easier to understand. And in 108e, I'll cover the gravitational Doppler effect. I may also cover other topics like rotating black holes and the Kerr metric later. When it comes to black hole solutions, we can categorize them for electrically charged.
I had a thought earlier today. I was taking a shower that I think might be good to share or to reflect on. Which is basically, I think I had this thought before, but it wasn't as clear as this time. Which is basically that the internet and technology can be viewed as applied information. The internet is the flow of electricity, so it can be viewed as the configuration of the electromagnetic field. And this flow of electricity becomes computation. And through the gates of computation, the electromagnetic field becomes abstraction. So if you think about it, the internet, there's the flow of electricity between cables connected all around the planet. And this electricity becomes computation when it reaches the computer, which is just configuration of electromagnetic field in these chips, which are the memory, and this the way the configuration of this electromagnetic field that becomes computation becomes abstraction through the people that absorb this information, and then it passes through another gate of decentralized computation, which is markets dynamics across the world. And because if you think about it, the market is just a decentralized computation of what's useful for society at any given moment in time in relationship to the environment. And yeah, the cost function of this loop, I think I'm getting ahead of myself, but so this becomes an abstraction, then goes through another gate, which is the markets, which are decentralized competition systems, and through that you have, uh, as a consequence, you have innovation and technology, and this technology shapes the space-time, closing back the loop. So you have the flow of electricity that becomes computation, that becomes abstraction, that becomes computation again through the decentralized system of the markets, the supply and demand. And as a result of that, it shapes the field itself again. And this is a asymmetrical feedback loop system because the relationship between the limbic system and the prefrontal cortex is asymmetrical. So in a way, the internet is like an exemplification of what happens on the individual level, because the individual is the same thing. Now you have impulses in your body. These impulses become computation on your brain, and your brain dictates your behavior according to the abstraction of your identity and the way you think about the past and future. And then, based on that abstraction, you're gonna have your actions and your behavior patterns that are gonna shift the impulses that you get from reality, because they determine where you are in your environment and how you act. And this is a feedback loop system, asymmetrical loop system. So in a way, the global dynamics of how human beings interact is just an exemplification of what happens in the individual level, because everything follows fractal patterns. So yeah, then I heard about something. Like I was talking on a podcast with Lex Friedman, the owner of co-founder of Instagram or something like that, and he said basically that people are not honest when they give feedback, and that's why they have to use data. And this gave me an insight, which I think is that the markets are the cost function of the collective consciousness. And the way that the cost function operates is through the limbic system. And that's the problem, because you have a decentralized computational system that is shaped by the flow of electricity and the configuration of electricity in space-time. And it is overfitted to the data. That's why we have the problem of, we have the chance of self-destruction, because the limbic system overfits the data sets in a mass scale. And I think that's the core of the issue here, because we are always adapted to things that already happened, because our abstraction shapes the reality faster than we can regulate it. And that's exactly the problem. You have a neural network at a global scale that is being shaped by the flow of electricity, and which is basically data. Electricity, electromagnetic field, and data, for me is pretty much the same thing. It's just abstraction is the filtering of that electromagnetic field into concepts and in organization of concepts, because it's a result of the computation over that electromagnetic field in relationship to the incentive. And in this case, the incentive is a consequence of the limbic system, which is the dopamine levels. So I think, yeah, that's pretty much it. But I'm not sure if this makes complete sense or if I'm seeing the things the wrong way. But I think the biggest problem is the way that the cost function works, which is determined by the incentives of the limbic system. So I'm trying to think about ways to measure this and maybe figure out what is the function, the cost function that the limbic system provides. And I think it has to do with the dopamine levels at a mass scale. And I think maybe it's possible to use the data from all these sites to determine what's the default, what's gonna be the default of human beings when faced with decisions. And I think the default's gonna be addiction. But I think the main thing is this correlation that flow of electromagnetic field is directly correlated to the cost function of the limbic system. And the exemplification of that is a market economy. So these things are directly correlated. I think the three fundamental pillars are flow of electromagnetic field, shape of space-time, which from this playlist has to do with geodesics and the structure of how these different reference frames are connected. So it's basically like a feedback loop system because everything has to be the bottom line of reality has to be infinity. So everything has to be a closed loop system. And I think that's the closed loop system of survival in the human species in relationship. So we have the geometry of space time, you have the flow of the electromagnetic field, and you have the regulation of this flow. You have this flow becoming computation through the limbic system that determines what the abstraction is going to shape the environment itself. So technology is a consequence of the flow of the electromagnetic field becoming market economy through the computation of the limbic system at a mass scale and becoming abstraction and shaping the environment itself. And maybe the best way to try to prevent self-destruction from exponential tech is try to figure out the correlation between this flow of electricity, computation, and uh, try to figure out what is the exactly this cost function. Are the how is the data, which is the electromagnetic field, being parsed through the space time and becoming abstraction and shaping itself. So I think that's a rough idea, but I still don't know, still don't have a clear picture of exactly what to do with that. So maybe I can write a couple of ideas here. I think one idea is to map out flow of internet. So try to get data on cables and the connectivity of the internet. Then study consumer behavior, data of cost function, which is gonna be the feedback loop system of consumers, which is basically like they say on the podcast of the Joe Rogan podcast with Tristan Harris. It's basically pretty much rage and fear that drives engagement and tribalism. So I think tribalism is the geometric structure, the fractal geometric structure of social behavior at all scales. And the way that this structure is going to be shaped is going to be by as a consequence of the environment. So you always have these fractal patterns, which is 80-20 distribution for productivity, which means that 20% of the people are leaders, 80% are followers, and you have this fragmentation of uh, groups based on the tribal behavior because the hardware of the human body is equipped to do with only 150 people maximum. So things break down at a global scale. And this geometric shape, the order of the different groups and what is considered to be normal and not normal in the laws and the regulations are basically the connection of, you can view it as a geometric structure. So regulations are the connection of molecules within the system. And I think that connection is going to be shaped by the electromagnetic field and the abstraction, because the abstraction shapes the space-time, which as a consequence shapes the electromagnetic field as well. Because I think that the electromagnetic field, the flow of the electromagnetic field is determined by the structure of space-time. So map out the flow of the internet, then study consumer behavior, feedback loop system of consumer tribalism. I don't know how to write this. Tribalism, which is the cost function. So basically, you can view the market economy as in the same way that you view a neural network trying to fit some data set. I think that's what markets are doing. You have data points coming in, which is the electromagnetic field, and the structure of the market is to find the relationship between these data points, which means how useful something is for our society. And that approximation is gonna be equivalent to the limbic system, to the way that the limbic system works, which is a problem because it's gonna overfit the data set because we are always behind what's happening. So that pretty much means that the market structure makes us overfit the data, and we have a misrepresentation at the collective consciousness level of reality, which means we can't handle new data inputs very well. Geometric structure of social. Yeah. I'm trying to think about how can I translate this into a system to make measurements and try to figure it out. So the biggest issue here, I think, is that you can't map out the abstraction because it's unpredictable. But maybe you can because imagination can only exist as a consequence of the things you already know. So maybe abstraction, you can predict innovation because it's always a consequence of the abstraction of the computational system. Because ideas are a consequence of the electromagnetic field. So maybe if you can map out the electromagnetic field and use data to understand how this field is shaping society through markets. Maybe you can predict what the innovation is going to be because you know what the incentive is for control and power. And maybe, and then from that, you can find a better distribution of this feedback loop system. So, so I think what I need to do is try to create a model of the geometry of social behavior. I was thinking about creating a graph. That's why I was studying the Twitter API because we can get connectivity and a graph of the representation of the social structure. And if you have historical data, maybe you can do that to find the correlation between the electromagnetic field and how the connections are changing over time. But of course, that wouldn't give the complete clear picture because the data is always incomplete and is always subjective by nature. So what's the first step? The third step. Then figure out, try to use step 1 and 2 to predict how abstraction is going to the shape space-time and consequently flow of electromagnetic field. This is pretty much impossible to do, and I don't think I'm actually going to be able to do this, but I don't see any other choice but to try to do it because we pretty much don't have any other option. If you can't make this happen, we all die, pretty much. Or not, maybe not we all die, but it's just impossible to predict what's gonna happen. I think the most likely scenario is that we all die because you can't control the. It's like you have to think about probabilities, and if you have too much decentralization of power, you're just increasing the probability that you're gonna have an event that causes self-destruction. And at any given social structure, you're always gonna have the probability, even though it's small, you're gonna have the probability of certain personality types and some situations that get triggered by the environment, like mass shootings and terrorism, is just a consequence of the way that the social structure is shaped, which is the step two here. Because human beings are a collection of probabilities, the personality, I believe that personality traits are consequence of the genetic mutation of the sun. which follows, for the most part, a normal probabilistic distribution or logarithm, logarithmic, I don't know how to say that, uh, distributions which are exponential. And then these distributions become exponential through this pattern of the interactivity of human beings through politics and economics as a consequence of the need to survive. So you have this oscillation, which is a wave function, which is genetic mutation determine the distribution of probability of personality types, which is a fractal pattern because every person is gonna be along the distribution of the normal probabilistic distribution of certain personality types, and the combination of those probabilities is gonna make up the individual. And as we know, this when you have a bunch of human beings, that the average is gonna be that you're gonna form groups because of that. Because even though everybody is unique, you have common trends, which are fractal patterns, because I think that's how the universe works. And then you're gonna have this structure where everybody, the flow of the social structure is always through a 80-20% distribution, but the shape of the personalities and genetics is a normal probabilistic distribution. And the changing complexity in the social structure is gonna be the oscillation between the two in relationship to the environment, because the environment is what's determined the pressure and the pain to change the structure. And the more power you have, the more delicate the balance begins, and the balance becomes. Yeah, I think that's the more delicate the balance becomes, because yeah, I still have to think about what is power and how it happens. I know that the increase in power increases how much the abstraction, the applied abstraction, which is technology, shapes the environment. And I think that's, yeah, that might be the function of society as a whole, because everybody wants to survive and reproduce. And the way to do that is by increasing the power. Because when you have more power, you can shape the environment in which you exist. So I think in a way, power might be the oscillation of these probabilities. So power equals frequency, the frequency of this shift. And this is this feedback loop system from electromagnetic field to through computation, through abstraction, through electromagnetic field, through space-time, then electromagnetic field. So I think the first step is try to create something like this that maps out this feedback loop system, and then understand the cost function of the limbic system. The second part is try to think about different ways to change the computation, because I think that's the main problem. It's the way that markets, the Nash equilibrium of markets in a global scale, in a local scale, makes us create things, the arms race, and the neglection of responsibility and incentive for sociopathy at a large scale. So I think first, the first part is understanding this flow from electromagnetic to information, and then once, if I'm able to understand this, then is to use this to try to create a different system that doesn't overfit the data sets. And maybe I believe also that, I'm not sure if this is true, but that the universe is half deterministic, determini- and half probabilistic. So in other words, you have some randomness, but you also have some stability, which is the law of gravity. But I don't think everything is fully predicted. So it also might be possible to understand how much variance exists in the universe. But it might not be the case because I don't understand really well how time comes through to be and the law of gravity still. So, so I'm gonna watch this playlist with that in mind, I think.
Charged and uncharged black holes, and rotating and non-rotating black holes. We're going to look at the uncharged non-rotating case, called the Schwarzschild solution. So we're now going to find the Schwarzschild solution to the Einstein field equations. But what exactly does it mean to solve the Einstein field equations? It basically means we put in an energy-momentum tensor T and solve for the metric G. So we put in a description of the mass, energy, and momentum in spacetime, and we get out a complete description of the geometry of spacetime. Using the metric, we can then solve the Geodesic Equation, which will give us the paths of massive objects and light beams through curved spacetime. So we'll know how gravity affects mass and light. So what type of energy-momentum tensor will we use to get our spacetime solution for a spherically symmetric mass? Well, we know inside the Earth we have mass and pressure, so the energy-momentum tensor inside the Earth is non-zero. But outside the Earth, we can assume spacetime is approximately a vacuum, so the energy-momentum tensor is zero. In this video, we're just going to focus on spacetime in the exterior vacuum region only. So we're going to set the energy-momentum tensor in the Einstein field equations to 0. We're also going to set the cosmological constant to 0, since it's basically negligible unless we're working at cosmological scales. If we take the trace of what's left, using the inverse metric to raise an index, the trace of the Ricci tensor is the Ricci scalar, and the trace of the 4x4 identity matrix is 4. So we end up with the Ricci scalar being 0. So for a vacuum region, the Einstein field equations simplify to just the Ricci tensor being 0, which we call a Ricci flat spacetime. Now, the vacuum outside the mass still involves curved spacetime, because the Riemann curvature tensor here is non-zero. But the Ricci tensor is 0, and this means there are no immediate changes in the volume of a group of test particles outside the Earth as they move along geodesics. We only get tidal forces that squash and stretch the test particles without causing any immediate changes in the volume. So our job is to take this equation and solve for the components of the 4x4 spacetime metric that describes the curved spacetime near a body of mass m. We're also going to assume that, as we move far away from the mass, the effects of gravity become negligible, and spacetime becomes basically flat, described by the Minkowski metric. Now, before I start solving for the metric, I'm going to do a quick review of spherical coordinates. You can look at the video timestamps to skip this section if you want. Since we're dealing with a spherically symmetric mass, it's better to deal with spacetime in spherical coordinates. So instead of using the spacetime coordinates ct, x, y, z, we'll use ct, r, theta, phi, as defined here, where r is the radius, theta is the angle from the North Pole, or co-latitude, and phi is the angle of rotation around the vertical axis. or longitude. And as a reminder, we'll sometimes denote these four spacetime coordinates using the 0, 1, 2, 3 indices, where 0 indicates time and 1, 2, 3 are the spatial dimensions. And in summations, when we use a Greek summation index, this refers to all four spacetime indices. But if we use a Latin or English letter for the summation index, this just refers to the spatial indices without time. If we change from the Cartesian coordinate basis to the spherical coordinate basis using multivariable chain rule and calculate the dot products of the basis vectors, we get these components for the metric tensor in spherical coordinates. The spatial dot products have negative signs in front because in our mostly minus convention for the metric, space-like vectors have negative squared lengths. Remember, the components of the metric tensor are just the dot products of the basis vectors in our spacetime coordinate system. So the metric tensor helps us measure lengths and angles in spacetime. So both of these metric tensor matrices represent flat Minkowski space, but one is for Cartesian coordinates and the other is for spherical coordinates. The reason you see coordinate variables like r and theta in the metric components is because the theta and phi basis vectors change length depending on their position in space. For example, the phi basis vector is bigger near the equator, and both the theta and phi basis vectors get longer as we move away from the origin. So this should be the metric far away from the mass, as r approaches infinity and spacetime becomes flat. But close to the mass, the metric components of the curved spacetime are unknown. We can use some assumptions to narrow down the exact form the metric components should take. First, we're going to assume that spacetime is static. The technically correct definition of static spacetime involves a concept called killing vectors, which I haven't covered yet. So I'm going to use a simplified definition. We'll take static spacetime to mean two things. First, the metric doesn't depend on time, and second, that spacetime is symmetric when we reverse the time coordinate. This is like mirror symmetry across the time axis. This guarantees the black hole isn't rotating, because if we reversed time for a rotating black hole, the gravitational effects due to rotation would also reverse direction. Since basis vectors are just partial derivatives with respect to a coordinate variable, reversing the direction of the time coordinate also reverses the direction of the time basis vector. This does not change the GTT metric component since the two new negative signs cancel out, but it will change the sign of ET dotted with any of the EI space basis vectors. Since GTI equals negative GTI, these metric components go to 0. If we want spherical symmetry in space, the theta and phi components of the metric should resemble the metric for a sphere of radius r. However, we also allow multiplication by a radial function c of r, since this doesn't violate spherical symmetry. I'm also going to make these terms negative since space-like vectors have negative metric components in the mostly minus metric convention. If we want the radial basis vector ER to stick out normal to the sphere in the radial direction, it must be perpendicular to both E theta and E phi. So these dot products and metric components go to 0. So under our assumptions so far, the metric is diagonal. The remaining GTT and GRR components should only depend on the radial coordinate r if we want to maintain spherical symmetry. So we'll call them A of r and negative B of r. We're using a negative sign since this metric component corresponds to a space-like direction. Now, to simplify things, we can always redefine the radial coordinate r to be r tilde equals r times the square root of c of r, and this would eliminate the function on the last two metric components. However, I'm not going to bother writing out r tilde everywhere, so I'm just going to rewrite the new radial component as r instead.
I just thought about something in relationship to the things I was talking about. I think this second map here, second part, study recommendation. I think these neural networks can give me picture of what's most likely the cost function for the limbic system. I think after I'm done with this playlist, I'm gonna watch videos based on that step-by-step thing. Those steps I
Just as a warning,
wrote there.
some texts might write these a and b functions as exponential functions instead. They do this because they already know that getting the right answer involves using terms like partial a over a, which becomes much simpler if you use exponential functions. But I'm not going to bother using this exponent trick in this video. So we've simplified the form of the metric as much as possible. In order to solve for a of r and b of r, we'll have to calculate the connection coefficients, calculate the Ricci tensor components, and then force the metric to give us the results of Newtonian gravity in the limit of low velocity and weak gravity. And this will give us the Schwarzschild metric. So let's start by calculating the connection coefficients. There are 13 non-zero connection coefficients in the Schwarzschild solution, and only 9 of them are independent. Calculating them is pretty boring, but necessary. I'll start by solving for the connection coefficients with a 0 upper index, then a 1 upper index, then the 2 and 3 upper indices. So here's the standard formula for the connection coefficients. Since the metric is diagonal, we can easily get the inverse metric just by taking the reciprocal of all of the diagonal elements, denoted by g with the upper indices. So here's the standard formula for the connection coefficients. But since we know that our metric is diagonal, its two indices always need to match if the components are to be non-zero. So we can rewrite the sigma alpha inverse metric with repeated sigma sigma indices to make it diagonal, and replace all other alpha indices with sigma. So this is not a summation over sigma here, it's just denoting that these two indices always need to be the same. Now let's look at the connection coefficients with 0 on top. With 0, 0 on the bottom, all the time derivative terms go to 0, since g00 doesn't depend on time, so we get 0. If both the lower indices are the same spatial index I, these metric components here are not diagonal elements of the matrix, and therefore they must be 0. From now on, I'm just going to cross out non-diagonal metric components without saying anything out loud, since it's going to happen a lot. This time derivative term is 0, since the metric components don't depend on time. And if the lower indices are both spatial but not equal, all the metric components are off-diagonal, so we get 0. In the case where one lower index is time and the other is spatial, this term survives. G inverse 0, 0 is 1 over a, and g00 is just a. This spatial I derivative can be any of partial 1, partial 2, or partial 3, or in other words, partial r, partial theta, or partial phi. Since the a of r function only depends on r, only the partial r term gives a non-zero result. So the lower 0, 1, and 1, 0 coefficients are non-zero, but 0, 2, and 0, 3 go to 0. So those are all the connection coefficients with a 0 index up top. Now let's continue to the coefficients with a 1 on top. For 0, 0 on the bottom, we get negative 1 over b here and the r derivative of a, giving this. For 1, 1 on the bottom, these cancel and we get negative 1 over b times the r derivative of negative b. With 2, 2 on the bottom, we get negative 1 over b and the r derivative of r squared, which is just 2r, so we get negative r over b. And for the 3, 3 on the bottom, we get the same thing multiplied by sine squared. When one of the lower indices is 1, all the coefficients go to 0, either because they're off-diagonal or constant with respect to a derivative. Any other mixed lower indices give all off-diagonal metric components, so they go to 0 too. So these are all the non-zero coefficients with 1 on top. For the 2 on top coefficients, having 0, 0, 1, 1, or 2, 2 on the bottom all give 0. But 3, 3 on the bottom gives us negative 1 over r squared for the inverse 2, 2 components, and the derivative with respect to theta of the 3, 3 component. The negative 1 over r squared and negative r squared cancel, and the derivative of sine squared is 2 sine times cosine. If one of the lower indices is 2, then having 1, 2 on the bottom gives us a non-zero term, which simplifies to 1 over r. Any other mix of indices on the bottom all go to 0. So these are all the non-zero coefficients with 2 on top. Finally, for the 3 on top coefficients, if we have repeated lower indices that are not 3, the off-diagonals go to 0, and the last term goes to 0 since the metric components don't depend on phi. and the 3, 3 lower indices go to 0 as well because nothing depends on phi. For 0, 3 on the bottom, we get 0. For 1, 3 on the bottom, we get the derivative of g3, 3 with respect to r, which is non-zero. Canceling sine squared and churning through the derivative and algebra, we get 1 over r. For 2, 3 on the bottom, g3, 3 depends on theta, and canceling r squared and working through gives us cosine over sine, which is the definition of cotangent. All the other mixed lower indices go to 0. So now we have all 9 of the independent non-zero connection coefficients. And even though I'm using the mostly minuses metric, all of these coefficients should be the same in both the mostly minus and mostly plus metric conventions. And if you want to view these connection coefficients as arrays, they would look like this. So given these connection coefficients, we're now going to calculate the formulas for R00, R11, and R22. Remember, our Einstein field equations tell us that all the components of the Ricci tensor are equal to 0. We'll see that these three equations will be enough to solve for our a and b functions. Remember, given the Riemann tensor, the Ricci tensor is just the Riemann tensor with its upper and lower middle indices summed together. So the 0, 0 Ricci component looks like this. Now, there are a lot of summations here, like the summations over mu, alpha, and beta. But it will turn out a lot of these summation terms go to 0. For each of the 4 terms here, we need to look at the non-zero connection coefficients and decide what the non-zero coefficients in these summations are. For example, the first term has 2 zero indices on the bottom of the connection coefficient, and there's only a single non-zero connection coefficient with 2 zero indices on the bottom, which is the 1, 0, 0 coefficient. So this means that even though the mu index is technically summed from 0 to 3, only the mu equals 1 term stays around. With this second term here, there are actually no coefficients with 0 on the lower right, with the other 2 indices matching. So it goes to 0. For the third term, looking at the alpha index, with 2 zeros on the bottom, alpha must be 1, for this to be non-zero. And for the fourth term, looking at the beta index, we see that beta could be 0 or 1, but not 2 or 3. So the beta summation expands to 2 terms. We still have some mu summations left. Here, mu could be either 0, 1, 2, or 3. So this expands to 4 terms. For the last 2 summations, mu must equal 1 in the first summation, and mu must equal 0 in the second summation. Now, this conveniently cancels with this, and since the 2, 2, 1 and 3, 3, 1 coefficients are equal, I'm going to group them as 2 times the same term. We're now ready to sub in the formulas for the connection coefficients. Most of these we can just multiply together, but this derivative term with the 1 coordinate, which is the r coordinate, involves product rule for the product of partial Ra and the reciprocal of b. We get the second partial derivative of a in the first term and use power rule on b to the negative 1 to get b to the negative 2 times negative 1 times a chain rule derivative term. Rewriting, we get this. Now remember, all of this is equal to 0, since the Ricci tensor is 0 in our solution. To make this easier to read, I'm going to replace the partial derivative of a with respect to r with a prime, and replace the partial derivative of b with respect to r with b prime. I'm also going to multiply the equation by a common denominator of 4ab squared r to get rid of the denominators. So that was r00. For r11 and r22, I'm just going to run through them quickly. You can pause the video if you want to check the algebra. For R11, we have mu equals 1 here and expansion to 4 terms, alpha equals 1 here and expansion to 4 terms. We get another expansion to 4 terms, and mu equals 0, 1, 2, 3 for the rest. Then we do some canceling, and grouping of like terms. After subbing in the coefficient formulas, we need to do product rule on the first term, and use power rule on 1 over r to get 1 over r squared times negative 1. We can then do some canceling and combine terms, and we multiply by 4a squared br to get rid of the denominators. For r22, we have mu equals 1, mu equals 3, alpha equals 1, and beta equals 1, 2, 3. This sum expands to 4 terms, and then we have mu equals 2, mu equals 1, and mu equals 3. Then we cancel, and factor like terms. After we sub in the formulas, we have to do the product rule on r times b to the negative 1, and also cotangent, which is just cosine times sine to the negative 1. So we have product rule and product rule. This is just plus 1, and this is cotangent squared. So we cancel, distribute, combine, and multiply by 2 times ab squared to get rid of the denominators. So all these Ricci components equal 0. This means that if we add r00 and r11, the result should be 0. If we sum these terms in r00 and r11, these cancel, and these cancel. So we get 4ab prime plus 4a squared b prime equals 0. If we cancel 4a from both terms, we get ba prime plus ab prime. This is just the product rule result from the derivative of a times b. And since this derivative is 0, this tells us that a times b is a constant, which I'll call capital K. Now, we know that as the Schwarzschild metric goes out to r equals infinity, it will approach the flat-Minkowski metric, where a equals 1 and b equals 1. So in this limit, a times b equals k becomes 1 times 1 equals k. And since k is the same constant for all r values, k equals 1 for all r. This means that b equals 1 over a for all r. So knowing the R22 formula, and that b equals 1 over a, and that b prime is the derivative of 1 over a, which is negative a prime over a squared, we can substitute in for b and b prime. If we cancel factors of a and add these together, cancel the 2's and rearrange,
Just thought about something. The biggest issue here with this is that you can't separate observer from what's being observed. So there's entanglement. Well, like which comes first, the data or the computation? I think the data has to be more fundamental. But maybe the data itself is a consequence of the computation, because the computation might be parsing infinity by a reference, right? That gives rise to space-time. So that's how I'm thinking about it. You have infinite potential, then you have the filtering of that infinity through the lens of the experience of reference frame. That becomes the true computation becomes an electromagnetic field, which is the experience of the observer. So in a way, data is the computation. But maybe space-time is more fundamental. Yeah, I'm not sure. I think electromagnetic field and space-time are in the same level. And computation is the approximation of the field. And that's why the double slit experiment. Because at the bottom level you have infinity, which has an element of unpredictability, and then it becomes gravity once it is perceived by a reference frame, which creates the portion of that infinity that is predictable, that is consistency, which is gravity. But then if that was the case, it wouldn't be possible to separate the two. Computation and electromagnetic field would be the same thing. So yeah, I still can think about the distinction of this two. I don't think they can be the same because otherwise computation would always be correct. Like you would never be able to. Well, but data is actually a representation, a sliced representation of the field. Because you're abstracting and simplifying all the information into concepts. So data itself is already the filter of the field through computation. But then what is a neural network doing? It's finding relationship between different parts of the field through the filters. I still can't think about it. Though.
We get the differential equation r times a prime equals 1 minus a. The solution to this equation is a of r equals 1 minus a constant small k over r. If we calculate the derivative of a, we find that it's k over r squared. And if we plug a prime and a into our differential equations, r's cancel here, 1's cancel here, and we get k over r equals k over r. So this solution satisfies the differential equation. So we've solved for a of r equals 1 minus k over r, and b is just 1 over a. So we have the form of the Schwarzschild metric. Now we just need to solve for the constant k, which ends up being 2gm over the speed of light squared. This is called the Schwarzschild radius, or the event horizon of the black hole. We can solve for the lowercase k constant by forcing the Schwarzschild metric to reproduce Newtonian gravity in the limit of low velocity and weak gravity. For this part of the video, I'm going to use the Minkowski metric in Cartesian coordinates instead of spherical coordinates. I showed in Relativity 107F, during the derivation of the Einstein field equations, that we can force the geodesic equation to match the Newtonian equation for acceleration due to gravity. In the limit of low velocity, the proper time is approximately equal to the coordinate time t, and an object's four-velocity vector components are dominated by the time component, which is basically c, with the other components going to 0. To get the geodesic equation to match Newtonian acceleration, we need the I00 connection coefficient to be 1 over c squared times the partial derivative of the gravitational potential phi in the I direction. Now, when we say we're taking the limit of weak gravity, this means that the metric can be written as a sum of the flat Minkowski metric eta plus a small change h, where the components of h are much less than 1. This basically means that when we do a summation with the metric, the h part is small enough to be ignored. But when we take the derivative of the metric, we ignore the constant Minkowski part in Cartesian coordinates and only get the derivative of the h part. So if we take the formula for the connection coefficients and look at the I00 case, this inverse metric can be approximated by the flat Minkowski metric, and these metric derivatives are equal to the derivative of the h part. And since the metric is diagonal, we know this alpha index must match the spatial index I if we want the components to be non-zero. The first two terms are off-diagonal and go to 0, and the space-diagonal elements of the Minkowski metric are all -1 in Cartesian coordinates. So we're left with gamma I00 equals 1/2 times partial I of h00. But recall that gamma I00 is just 1 over c squared partial I of the gravitational potential. If we remove the derivatives on both sides, we see that h00 is just 2 times the gravitational potential over c squared. In Newtonian gravity, the gravitational potential for a spherical body of mass m is -g times m over r. This is what gives us the standard Newton's law of gravity after taking the gradient and multiplying by a second mass. So h00 equals -2gm over c squared r. So since we've solved for h00 in Cartesian coordinates, we've also solved for h00 in spherical coordinates, since both coordinate systems use the same time coordinate. Comparing this to the form of the g00 component of the metric that we've derived, the constant small k must then be equal to 2gm over c squared, which we can plug into the formula for the g11 component as well. This component, 2gm over the speed of light squared, is also called the Schwarzschild radius, and is often denoted by r subscript s. This completes the derivation of the Schwarzschild metric. One last thing before I conclude. A few slides ago, some people might point out that canceling derivatives on both sides here doesn't make sense, and the correct thing to do is to integrate both sides, which gives an additional constant of integration, giving this for h00 and this for g00. But since we want the metric to reduce to the flat Minkowski metric as r goes to infinity, we're forced to set this integration constant to 0. This is similar to how the Newtonian gravitational potential, -gm over r, can also have an extra constant added onto it, because the constant goes away when we take the gradient. This constant is the potential's value at infinity, so this value must be 0 if we want the potential to be 0 infinitely far from the mass. So to summarize this video, we derived the Schwarzschild metric, which is the spacetime metric for a spherically symmetric, uncharged, non-rotating mass, together with the additional assumption that spacetime is static, meaning in our coordinate system the metric doesn't depend on time, and also spacetime doesn't change when we reverse the direction of the time coordinate. This solution is only valid in the vacuum region outside the mass, not within the mass itself. And we also treat the cosmological constant as being negligible. In the next video, we're going to interpret what this metric means, and we'll see how it results in gravitational time dilation, how it affects light, and how the Schwarzschild radius Rs is interpreted to be the event horizon of a black hole, which is a radius beyond which light can never escape. In the last video, we derived the Schwarzschild metric for the curved spacetime around an uncharged, non-rotating spherical mass. In this video, we're going to interpret what this metric means. We're going to look at the physical meaning of the r and t coordinates, how we get gravitational time dilation for observers at different distances from the mass, and give physical meaning to the Schwarzschild radius Rs as the event horizon, a surface beyond which light can never escape. An important idea in this video is that the coordinates we put on spacetime geometry, like t, r, theta, and phi, don't always have an obvious physical meaning, and we should not trust them to give us important physical information. We should only trust the metric tensor g to properly make measurements of time and space. Let's start by talking about the time coordinate ct, and how it relates to the gravitational time dilation for observers at different distances from the spherical mass. In this video, I'm only going to cover radial motion near near the mass, so motion that goes directly toward or away from the mass along the r coordinate. This means I'm going to ignore the theta and phi angle coordinates, and I can treat space-time as two-dimensional, with only a time coordinate ct and a radial coordinate r. So I'm only going to use the ct and r entries from the Schwarzschild metric. On a space-time diagram, the center of the mass would be located at r equals 0 as it moves through time, where time points upward on the space-time diagram. Given these coordinate lines for ct and r, the tangent vectors along these lines would give us the basis vectors et and er, which are the partial derivatives with respect to the ct and r coordinates, respectively. Now, looking at this space-time diagram with our eyes, we might assume that all these time basis vectors are the same length, but that's actually not true. In relativity, we should never trust our eyes or trust space-time coordinates for making measurements. Instead, we need to trust the metric, which is the Schwarzschild metric in this case. The squared length of the ET basis vector is ET.ET, which equals the GTT component of the metric, which is 1 minus RS over R. So the length of all these time basis vectors depends on their R coordinate in spacetime. So let's take a look at the lengths of all these time basis vectors in different parts of our spacetime diagram, where this vertical dashed line is the mass's Schwarzschild radius. As R goes to infinity, very far away from the mass, RS over R goes to 0, so the squared length of the ET basis vector goes to 1, as we move infinitely far from the mass. As we approach the Schwarzschild radius RS from the outside, the length of the ET basis vector gets smaller and smaller, but its squared length is still positive. It's worth noting that, outside the Schwarzschild radius, the ET basis vector has a positive squared length, and so it's a time-like vector. Directly on top of the Schwarzschild radius, where RS equals R, the GTT component becomes 1 minus 1 equals 0. This means that on the Schwarzschild radius, the ET basis vector is a light-like vector, and points along the world line of a light beam. When R is less than the Schwarzschild radius, the squared length of ET becomes negative, meaning it is now a space-like vector, and observers can freely travel along it in the positive and negative directions. The idea that ET can be light-like or space-like is probably pretty confusing, but I'll discuss the meaning of this later in the video. For now, let's just focus on the region outside of the Schwarzschild radius, where ET is time-like, and its squared length is positive. Since the length of the ET basis vector is different for each r position, this means that observers moving through time at various constant r values will experience time differently. We also saw a similar effect in Relativity 105b, in flat space-time, in the accelerated reference frame given by the Rindler coordinate system. Observers at different constant x values in Rindler coordinates experience different amounts of proper time for the same amount of coordinate time, because the lengths of their time basis vectors are different. Although the effect is not the exact same because the Rindler metric and the Schwarzschild metric have different TT components. To calculate the total proper time along a world line parameterized by a path parameter lambda, we break up the world line into small pieces, measure each piece using the metric, and add the results together. In the limit of infinitesimally small pieces, this is the same thing as integrating over the length of the curve's tangent vectors d by d lambda, which is the square root of the tangent vector dotted with itself. So let's use the Schwarzschild metric to calculate gravitational time dilation. We can use multivariable chain rule to expand the tangent vector in terms of the spacetime coordinates. And in the special case of spacetime motion along a constant r value, these go to 0. And since we're free to use any path parameter that we like, we can just set lambda to ct. These go to 1, and we get the square root of gtt. Since the gtt component of the metric only depends on the r variable and not the t variable, we can bring it outside the integral. And the integral of dct just becomes ct. So we find that we can't just read time along a world line from the ct coordinate. Instead, there's a conversion factor between t and the proper time, and this conversion factor depends on the r coordinate. If we compare the gravitational time dilation formula to the kinematic time dilation formula from special relativity, we find that the velocity term corresponds to the escape velocity for the mass at a given radius, the square root of 2mg over r. Very far away from the mass, as r goes to infinity, the conversion factor becomes 1. So very far away, coordinate time t and proper time tau are the same thing for a constant r position. But the closer we go to the Schwarzschild radius, the smaller this conversion factor becomes. So the same amount of coordinate time results in much less proper time. For example, at a distance of 2 Schwarzschild radii, the conversion factor becomes the square root of 1/2, which is about 0.7071. So the proper time for someone at a distance of 2 rs is equal to the square root of 1/2 times the coordinate time, where the coordinate time is basically the proper time for someone at an infinite distance away from the mass. This means that 100 years for someone far away is experienced as only 70 years for someone hovering at a distance of 2 Schwarzschild radii. This is the effect of gravitational time dilation, where observers at different constant distances from a mass experience different proper times. As a consequence, if we have one observer at a constant position r1 and a second observer at a constant position r2, we can directly compare their respective proper times by taking the ratio of their gravitational time dilation formulas and cancelling the CT coordinate. Now, it should be noted that this simple relationship only holds for the special case of observers at constant r coordinates and constant theta and phi coordinates. Under the influence of only gravity, these observers would naturally fall towards the mass. So these observers must be using rockets to maintain their constant r position, or else they must be standing on the surface of the mass itself, held upward by the electromagnetic forces of the mass's particles. This means that all observers at constant r coordinates must have a non-zero 4 acceleration vector that's pushing them away from the freefall geodesics that lead towards the mass. So they would all measure a non-zero proper acceleration on an accelerometer that they are carrying with them, just like the accelerometer on the cell phone of someone standing on Earth measures non-zero proper acceleration. If we introduce motion that's infalling or outgoing, or angular orbital motion, this simple relation between t and tau no longer holds true. The correct way to compare proper time along two arbitrary world lines is always to integrate the tangent vectors along those world lines and compare the resulting proper times. Now let's look at the physical interpretation of the r-coordinate. The r-coordinate helps us measure distance, but as you can probably guess from the GRR component of the metric, the r-coordinate doesn't directly represent physical distance L0, which is also called proper distance or proper length. The proper distance between 2 points in space is the distance we would get if we laid out a series of meter sticks end to end between the 2 points. We calculate proper length L0 by integrating the tangent vectors along a curve, but this curve must be space-like, where the squared length of the tangent vectors are negative. We can again expand the tangent vector using multivariable chain rule, then use the special case where the t-coordinate is constant, and take the r-coordinate to be the path parameter, with these going to 1, and then we get the square root of negative GRR. After we sub in the GRR component, we see that we have a problem. This factor depends on r. And since the integral is over the r variable, we can't just pull this factor out of the integral. So in flat Minkowski spacetime, the proper length between 2 points A and B along an r-coordinate line is exactly equal to the change in the Minkowski r-coordinate value between the 2 points. But in Schwarzschild spacetime, there's a more complicated relationship between the Schwarzschild r-coordinate and proper length, involving this integral. We can see that a small proper length dl0 is related to a small change in the r-coordinate dr by this square root factor. When the r-coordinate is much larger than the Schwarzschild radius, this conversion factor goes to 1. So far enough away from the mass, the r-coordinate difference between 2 points is equal to the proper length between those 2 points. But as we get closer and closer to the Schwarzschild radius, this conversion factor gets larger and larger, meaning 1 unit of r corresponds to more than 1 unit of proper length. This means that the region of our spacetime diagram that's close to the Schwarzschild radius contains much more physical space than the region far from the Schwarzschild radius, even though it doesn't look like it on our spacetime diagram. We can see this concretely if we actually compute this integral. According to the free online textbook Exploring Black Holes, we can compute this integral by performing the substitution r equals z squared. And originally I wasn't able to do this integral, but my boyfriend showed me how to do it using a trig substitution, so special thanks to him for his help. And you can pause the video if you want to go through it yourself. We change variables to y to turn this into a 1, do another substitution with hyperbolic cosine, change back to y, use this identity to convert inverse hyperbolic cosine to a natural logarithm, plug that in, do some algebra, change back to z, and finally change back to r, absorbing this constant into the constant.
It's kind of crazy. Never assumed that this guy is gay.
Of integration, which goes away when we plug in integral limits anyway.
Very interesting.
We end up with this equation for proper length, to be evaluated at 2 r positions. Note that this formula is only valid in the spacetime region outside of the Schwarzschild radius. If we take a high point of r equals 3 Schwarzschild radii and a low point of r equals 2 Schwarzschild radii, this is a change in 1 rs in the r-coordinate. But our proper length formula tells us this is actually a change of 1.3 rs in actual proper length, which is larger. And if the high point is 2 rs and the low point is 1 rs, the change in the r-coordinate is again 1 rs. But the actual proper length is 2.3 rs, which is even larger. So we can see that, as we approach the Schwarzschild radius, 1 unit of the r-coordinate is worth larger and larger amounts of proper length. If we plot this function for proper length and compare it to the flat space case where r equals proper length, we can see that there's an obvious difference near the Schwarzschild radius. But if we zoom out, at the scale of 100 Schwarzschild radii or more, There's very little difference between the r-coordinate and the actual proper length from flat spacetime. So practically speaking, when we're far away from an object's Schwarzschild radius, we can act as if the Schwarzschild r-coordinate is measuring true physical distances in space. We only start seeing noticeable differences between the r-coordinate and proper length when we're close to the mass's Schwarzschild radius. Another way to understand the Schwarzschild r-coordinate is to look at how it relates to the circumference of circles around the mass. If we were to take a constant time, constant r, and constant angle theta of pi over 2 and allow the angular phi coordinate to vary, we can compute the proper distance around a circle. We can do this through our typical process of integrating over the lengths of tangent vectors, in the special case where only the phi variable changes and all the other variables are constant. Using phi as our path parameter, we get the conversion factor between phi and proper length to be the square root of negative g phi phi. Looking at the metric, g phi phi is just negative r squared sine theta squared. But sine theta goes to 1 since theta is just a constant of pi over 2. We can pull r out of the integral, and the integral of d phi is just phi. This is an interesting result because r times phi is the standard circle arc length formula that we see in flat space. For example, for an angle of phi equals 2 pi, we get the standard formula 2 pi r for the circumference of a circle around the mass. So even though the r-coordinate doesn't directly measure the physical radius to the mass, it does accurately measure the circumference of circles around the mass according to the standard flat space arc length formula, r times phi. So in Schwarzschild spacetime, given a circle around the mass, radial distances inside the circle are larger than we'd expect in flat space, given the circle's circumference. So essentially, near the Schwarzschild radius, space is bigger on the inside. This is explained by the curvature of space itself, so that the distance between concentric circles is increased due to the curvature of space. The surface traced out by these circles is called Flam's paraboloid. It represents a two-dimensional slice of space at constant ct and theta equals pi over 2. So where only r and phi are allowed to vary. The third dimension in this diagram doesn't correspond to anything physical, but it helps us visualize the curvature of space, so that the distances we see with our eyes actually correspond to the real distances in curved space. Far from the mass, space is almost flat, which is why the r-coordinate very nearly matches proper distance. But space gets significantly more curved close to the Schwarzschild radius. You can check the links in the description to learn more about Flam's paraboloid. The last thing we'll do in this video is to give an interpretation to the Schwarzschild radius Rs, which corresponds to the event horizon of a black hole. You might have noticed that one of the components of the Schwarzschild metric goes to infinity when r equals 0, and another component goes to infinity when r equals rs. We call these points singularities. It turns out that the r equals 0 singularity is a true singularity in the geometry of spacetime. It's a point where the manifold of spacetime comes together in a pinch and just stops, and our theory of general relativity doesn't make sense anymore. But the singularity at Rs is not a true geometric singularity. It's just a singularity resulting from our choice of coordinate system. You might notice that in 2D polar coordinates, the coordinate system stops making sense at the origin, because any value of the angle coordinate gives the same point, and the radius r can't become negative. This means that coordinate derivatives and basis vectors don't make sense at the origin. But this is not because of the geometry of the flat 2D plane. It's only due to the choice of coordinate system we've used. If we change to Cartesian coordinates, the origin has derivatives and basis vectors defined on it just fine. The singularity at r equals rs in the Schwarzschild coordinates is exactly this type of coordinate singularity that results from the Schwarzschild coordinates. We can describe the same Schwarzschild geometry in other coordinate systems, like Kruskal-Szekeres coordinates, where the Schwarzschild radius no longer causes a coordinate singularity. But I'm going to cover that in a later video. For now, we'll just do the best we can with the Schwarzschild coordinates. So we know that the Schwarzschild radius rs is 2gm over c squared. It only depends on the mass of the object and some physical constants. Since g is very small and c squared is very big, the Schwarzschild radius is very small for most objects. For example, the Schwarzschild radius for the Earth is only about 1 centimeter, and the Schwarzschild radius for the Sun is only about 3 kilometers. Both of these are deep inside the physical radius of each body. When an object is so incredibly massive and dense that its Schwarzschild radius becomes larger than its physical radius, we call this object a black hole, and we call the Schwarzschild radius the black hole's event horizon. If we imagine a super dense object like this, we could understand how it curves space-time by calculating how light behaves near it. In other words, we could calculate the light-like geodesics, which are the geodesics where all the tangent vectors have a squared length of 0. To make things simple, we are only going to consider light beams traveling in a radial direction, so directly toward or away from the mass, with constant theta and phi coordinates. So if we take the squared length of the tangent vector to be 0 and expand in terms of spacetime coordinates, we get this formula with the metric. Normally the metric is 4 by 4. But if we assume radial motion only, we can ignore the theta and phi coordinates and assume a 2 by 2 metric, which gives us this formula if we plug in GTT and GRR. If we move this term to the other side, then multiply both sides by 1 minus rs over r, we get this, and we can take the square root of both sides to remove the squares, and get a plus or minus sign. Again, the path parameter lambda can be anything we want, So let's choose lambda equals ct, which means this goes to 1 and we get this. So if we multiply both sides by c, it kind of looks like the distance over time derivative is telling us that the speed of light is changing by this factor here. So you might wonder if this means the speed of light is changing due to gravity. Well, it depends on what you mean by speed. Again, we can only trust the metric for making physical measurements. We can't trust our eyes or trust the r and t coordinates. We know the t coordinate is the proper time for someone infinitely far away from the mass, and r does not measure proper length. So dr by dt is just a ratio between coordinates, and it doesn't always have any particular physical meaning. However, the local speed of light, which is the derivative of proper distance with respect to proper time, is always equal to c. This is an objective fact that is true for all spacetime geometries and all coordinate systems. We saw something similar in Relativity 105F, where an accelerated observer in flat spacetime saw light beams with changing slope in Rindler coordinates. But the local speed of light, dl0 by d tau, was still c. So given this relationship for the paths of light beams in Schwarzschild coordinates, if we take the reciprocal of both sides and multiply by r over r, we get this differential equation, which has a solution involving log. When I write log, I'm talking about log base e, or what some people call the natural logarithm, or ln. So if y equals log of u, this means that u equals e to the y, and also the derivative of log u is 1 over u. We can calculate the derivative of this solution to confirm it satisfies the differential equation. Taking the derivative of ct with respect to r, this goes to 1. The derivative of this constant k goes to 0. And the derivative of log gives us 1 over the input of the logarithm, times a chain rule term, which is just dr by dr, which is just positive 1. We can replace this plus or minus 1 with plus or minus r minus rs over r minus rs. And this rs and this rs always have opposite sign, regardless of whether we select the plus solution or the minus solution. So they cancel. And we get plus or minus r over r minus rs, which can also be written as plus or minus 1 over 1 minus rs over r, which is the derivative we were expecting from our differential equation. So this is a valid solution. So this solution has a linear part, a logarithmic part, and a constant part. If we graph the linear and logarithmic functions, we see that the logarithmic function changes very quickly when its input is close to 0, but very far away from 0, it doesn't change very much. So when we add the linear and logarithmic functions together, we expect the logarithmic part to dominate when the log input is close to 0, and for the linear part to dominate as we move farther and farther away. If we plot a bunch of light beams going into the mass, which corresponds to the negative sign here, with different starting constants, we get curves like this. The Schwarzschild radius rs is where the input of the logarithm becomes 0. So all the ingoing light beams bunch up here. So according to these geodesics, these light beams never actually cross the Schwarzschild radius. Even if an observer far from the mass waits a really long time, gravitational time dilation means this long amount of time corresponds to smaller and smaller proper times for objects near the Schwarzschild radius. Clocks here tick slower and slower, such that nothing will ever cross the Schwarzschild radius from the perspective of an outside observer. Things will just freeze slightly before the crossing point. The reverse is true for outgoing light beams, which correspond to the plus sign in our solutions. According to an outside observer, light beams near the Schwarzschild radius appear nearly stuck in place due to time dilation, but eventually they escape and return to their expected trajectory when spacetime becomes flat again. It's important to remember, though, that observers near the Schwarzschild radius won't notice anything strange going on with light. According to them, the local speed of light, which is proper distance over proper time, is still c. It's only observers far away from the Schwarzschild radius that observe slowly ticking clocks for clocks near the Schwarzschild radius. Now, what about light beams that are in the region inside the Schwarzschild radius? These have a very similar solution to the same differential equation, except we swap the signs of r and rs inside the logarithm, so their difference stays positive. Taking the derivative leads to the same final result because the minus sign cancels with a chain rule term. Plotting both the plus and minus solutions, we get light beams that look like this. All of these geodesics point towards the black hole's singularity at r equals 0. This means that, if light gets inside the black hole's event horizon, it is a mathematical impossibility for light to get outside again. Every single light-like geodesic inside the event horizon travels into the singularity no matter what. If we look at the light cones outside the event horizon on our spacetime diagram, they appear to get more and more squished as we approach the event horizon. This makes sense because we know the Schwarzschild r-coordinate represents larger proper lengths closer to the event horizon. On the event horizon itself, the light cone collapses to a vertical line. The meaning of this would be more clear in another coordinate system, but this basically means that outgoing light beams get stuck at a constant r-coordinate when they are exactly on the event horizon. Inside the event horizon, the light cones flip sideways and point towards the singularity at r equals 0. We can understand this by looking at the squared length of the time basis vector. Outside the event horizon, the squared length of the ET basis vector is positive, meaning ET gives a time-like direction. On the event horizon, the squared length is 0, so ET points in a light-like direction. And inside the event horizon, the squared length is negative, meaning the t-coordinate is space-like, and we can travel along it in either direction. If we look at the squared length of the r basis vector, outside the event horizon it's negative, and so the r coordinate is space-like. It is undefined on the event horizon in this coordinate system, and inside the event horizon the r coordinate is time-like, so all massive objects are forced to travel along the r coordinate in the direction of the light cone. So inside the event horizon we have a strange switching of roles where the t coordinate is space-like and the r coordinate is time-like. This is another situation where we can't trust coordinates to have obvious physical meaning. The strange swapping of the roles of the t and r coordinates is the result of the coordinate system we're using. But we can trust the metric tensor to tell us that, inside the event horizon, the r basis vector gives a time-like direction with positive squared length, and the t basis vector gives space-like directions with negative squared length. Now, you might still have some additional questions, like how do we know that light-like geodesics inside the event horizon always face inward instead of outward? Or how do we know the light-like geodesic on the event horizon corresponds to an outgoing geodesic instead of an inward geodesic? These questions will be answered in Relativity 108D when we look at alternative coordinate systems for Schwarzschild geometry, where we can clearly see light beams crossing into the event horizon and how light beams inside the event horizon can never escape and are doomed to head into the singularity. So to summarize this video, we learned that we can't always rely on coordinates on a space-time diagram for direct physical meaning. Instead, we should always rely on the metric to give us physical measurements of time and space. We learned that the Schwarzschild t coordinate corresponds to the time measured by someone infinitely far away from the spherical mass in the Schwarzschild geometry, and that this time coordinate corresponds to smaller and smaller amounts of proper time for someone who is closer to the mass. This effect is called gravitational time dilation. We also learned that the Schwarzschild r coordinate doesn't match directly with physical lengths, also called proper lengths, and that one unit of the r coordinate closer to the mass corresponds to a physical length that's longer than one unit. However, the r coordinate does give an accurate physical circumference of a circle surrounding the mass, using the simple arc length formula r times phi that we're used to in flat space. This means that there is a larger physical radius than expected for a given physical circumference, according to flat geometry. So we conclude that space itself becomes more curved as we move closer to the mass. Finally, we said that when a mass's Schwarzschild radius becomes greater than its physical radius, we get a black hole. From the perspective of an outside observer, light and massive objects that fall toward a black hole never appear to cross the event horizon due to the increasingly large effects of gravitational time dilation. An outgoing beam of light directly on the event horizon will remain frozen in place, and inside the event horizon, all light beams and masses are forced to fall into the singularity, because all time-like and light-like geodesics fall into the singularity, so it's a mathematical impossibility for anything to escape. In the next video, we'll calculate a wider variety of time-like and light-like geodesics in Schwarzschild geometry, and see how massive objects and light beams orbit around masses. In this video, we're going to derive the geodesics for the Schwarzschild geometry. These are the paths that massive objects and light beams will take in the curved spacetime near a spherically symmetric, electrically neutral, non-rotating body. So basically, this is how the gravity of planets, stars, and black holes affect light and mass. We're going to see some gravitational effects that don't happen in Newtonian gravity and are unique to general relativity, like gravitational lensing of light around massive bodies and the perihelion shift in the orbit of massive bodies, like Mercury's orbit around the Sun. These were both early tests of the accuracy of general relativity after it was proposed by Einstein. So in this video, I'm going to give a quick review of geodesics, then review gravitational orbits in Newtonian spacetime, then derive Schwarzschild geodesics, then compare the orbits of bodies in Newtonian gravity and general relativity, which includes discussion of how gravity affects light and also the perihelion shift of orbits. You can feel free to look at the video timestamps and skip ahead if you want. So now I'll give a quick review of geodesics based on what I said in Relativity 105F. A massive particle's world line through spacetime can be parametrized by its proper time tau. The tangent vectors with respect to tau are the particle's four-velocity vectors u. The four-velocity is a time-like vector, meaning its squared length is always positive, and it always lives inside the light cone because massive objects can't travel faster than light. The rate of change of the four-velocity vector with respect to proper time tau is the particle's four-acceleration vector a. The four-acceleration is a space-like vector, meaning its squared length is always negative, and it always lives outside the light cone. The square root of the negative squared length of the four-acceleration vector is the particle's proper acceleration alpha. This is the number that the particle would measure on an accelerometer that it's carrying along with it. A particle with no forces acting on it has a zero four-acceleration vector, and it follows a path through spacetime called a geodesic, which is sort of like the straightest possible path through spacetime. In general relativity, gravity is just the natural motion of objects traveling along geodesics through a curved spacetime. An object orbiting a planet, or freely falling down towards the planet, will both measure no proper acceleration on their accelerometers, so these are traveling along geodesics in spacetime. An object that's in deep space firing its rockets, or an object that's sitting on a planet's surface, would both have a non-zero reading on an accelerometer. These objects are not traveling along a geodesic. The object in deep space with rockets firing has a four-acceleration vector that's pulling it away from a geodesic path. And the object sitting on the planet's surface has the molecular forces of the planet's particles forcing it upward, away from a geodesic that would normally pull it towards the planet's center. So setting an object's forward acceleration vector equal to 0 gives us the geodesic equation, which can be written in several different ways. Solving the geodesic equation gives us the paths of freely falling particles through spacetime that are only affected by gravity and no other forces. Now, light beams are massless and always have a proper time of 0 by definition, so we can't define a forward velocity vector or forward acceleration vector for light. Instead, we parameterize light-like paths by a generic path parameter lambda, which gives tangent vectors d by d lambda along the light world lines. These tangent vectors always live directly on the light cone, so they are called light-like vectors, or null vectors, because their squared length is 0. A light-like geodesic is a geodesic where every tangent vector along the path is light-like, so the rate of change of these tangent vectors is 0. This gives us another geodesic equation that's parameterized with a generic path parameter lambda instead of proper time tau. It turns out that using a generic path parameter lambda instead of proper time tau gives us a geodesic equation that works for both massive particles and massless light beams. So massive particles follow geodesics with time-like tangent vectors, and massless light beams follow geodesics with light-like or null tangent vectors, but both light and massive objects obey the same geodesic equation. Our goal for this video will be to take the geodesic equation and use it to solve for the paths of massive particles and massless light beams through Schwarzschild spacetime, where the curved spacetime is caused by a spherically symmetric, non-rotating, uncharged mass. Before we look at geodesics in general relativity, let's do a quick review of gravitational orbits in Newtonian gravity. Let's say we're looking at the coordinates of a planet orbiting a star, using the 2D polar coordinates r and phi. The planet's position vector is capital R, and its velocity vector is d capital R by dt, where t is the universal Newtonian time coordinate. The basis vectors for this coordinate system, er and e phi, are just the partial derivatives of the position vector with respect to r and phi. Using multivariable chain rule, we can expand the velocity vector in terms of the radial coordinate r and the angular coordinate phi. And here I'm going to denote time derivatives using an overhead dot above the variable. And the derivatives of the position vector with respect to the coordinate variables give us the basis vectors er and e phi. The squared magnitude of the velocity vector is just the dot product of the velocity vector with itself. Using the metric for polar coordinates, where er has length 1, er and e phi are orthogonal, and e phi has length r, so this dot product gives r squared, we get this formula for the squared velocity magnitude. We know that this planet's angular momentum vector L is just the cross product between its position vector capital R and its linear momentum p, which is mass times its velocity vector. If we sub in our formulas for the position and velocity vectors and distribute over the cross product, we know that the cross product of a vector with itself is 0, so er cross er is 0, and the cross product of er and e phi is a vector perpendicular to them both, whose length is equal to the area of the parallelogram formed by er and e phi. This area is 1 times r, since e phi has length r, and the perpendicular vector is ez. So the radial velocity doesn't contribute to angular momentum, only the angular velocity does. And rearranging, we see that the magnitude of the angular momentum L over mr squared equals phi dot. We know the total energy of the orbiting planet is just its kinetic energy, 1/2 mv squared, plus the potential energy, which is mass times the gravitational potential function v of r. In previous videos, I wrote the potential as phi, but in this video, I'm going to write it as v. We can sub in our formula for velocity squared, then distribute 1/2 m, then sub in our formula for phi dot, then do some canceling. We can also use the standard Newtonian potential for a mass capital M, which is negative g capital M over r. Now, we see that in polar coordinates, kinetic energy actually depends on the r coordinate position. We can group this r-dependent kinetic energy term together with the r-dependent potential term, and call the combined terms the effective potential, v sub f. This is our main equation of motion for gravitational orbits in Newtonian gravity, where E is the constant total energy and L is the constant angular momentum. Technically speaking, these two terms give kinetic energy, and this term gives potential energy. But in this video, I'm going to treat this term as the effective kinetic energy because it depends on r dot. And I'll call these two terms the effective potential energy because they depend on r. For now, we're going to put this equation aside and derive the geodesics in our new theory of gravity, general relativity. We're going to find that the equation describing the orbit in general relativity is nearly the exact same as in Newtonian gravity, but with some slight changes. So our geodesic equation is actually 4 separate equations, one for each spacetime coordinate. This sigma index can refer to any of the 4 spacetime variables, ct, r, theta, and phi. To make our lives easier, we're going to assume our geodesics have a constant theta value of theta equals pi over 2, meaning the orbit is in the plane of the equator in our coordinate system, and all theta derivatives go to 0. We're allowed to make this assumption because our central mass is spherically symmetric, and we can always rotate our coordinate system so the orbit is in the plane of theta equals pi over 2. Now, in Relativity 108a, I wrote out the Schwarzschild metric in terms of 2 functions, a of r and b of r. And then we determined that a equals 1 minus rs over r, where rs is the Schwarzschild radius. and b is 1 over a, which can be written as r over r minus rs. If we calculate the derivatives of a and b, we can sub them in to get formulas for the connection coefficients TTR, RTT, RRR, as well as R theta theta and R phi phi. So we now know all 9 non-zero connection coefficients for the Schwarzschild metric, written as explicit functions of r and theta. Now you'll notice that our Schwarzschild metric only depends on r and theta, but doesn't depend on time or phi. This is a hint that there are conserved quantities associated with the time and phi variables. A more technical discussion of this involves killing vectors, but I won't discuss that in this video. So our time and phi geodesic equations will give us conserved quantities. The r geodesic equation will give us an equation for tracking the orbiting body's radial distance. And because we're using a constant theta equals pi over 2 coordinate, the theta geodesic equation just becomes 0 equals 0. Let's start with the time geodesic equation. To write out this summation over mu and nu, we need to find all the connection coefficients with t on top. There are only 2 connection coefficients with t on top, which are the TTR and TRT connection coefficients. And they both equal each other, so I'm just going to write this sum as 2 times gamma TTR, matching t with a time derivative and r with an r derivative. And we can replace the TTR coefficients with this, and then cancel the 2 and 1/2. We can show that this equation tells us that this quantity, the derivative of ct times 1 minus rs over r, is a constant of motion that doesn't change along geodesics. To see this, let's take the derivative of this quantity. We use product rule and get the derivative of the derivative in the first term, and the derivative of 1 minus rs over r in the second term. The derivative of 1 is 0, and we can use power rule on the derivative of r to the negative 1 to get r to the negative 2 with a minus 1 in front, times a chain rule term. These negative signs cancel, and if we write this 1 as r over r, we get an equation that's equivalent to the right-hand side of our time geodesic equation, which equals 0. So if this equals 0, we just multiply by the reciprocal of this term, cancel r, and we get our original geodesic equation. So since the derivative of this term equals 0, it is a constant quantity along geodesics. This constant is sort of like the energy per unit mass, which we will denote by curly E. If we look at this constant of motion very far away from the mass as r approaches infinity, and rewrite dt by d tau as gamma, and multiply by mass, we see that this value is the time component of the four momentum vector from special relativity. So this is one reason why we refer to this constant of motion as energy. For the r geodesic equation, we get 4 connection coefficients with r on top. And since theta is constant, the theta derivative goes to 0. If we plug everything in, this sine theta goes to 1, but we still get a pretty complicated equation. We're actually not going to worry about this equation in this video. For the theta geodesic equation, there are 3 connection coefficients with theta on top. And if we assume theta is a constant of pi over 2, with these derivatives being 0, this equation just becomes 0 equals 0. This is a good thing, because it tells us that a constant value of theta equals pi over 2 does not violate our geodesic equations, so it's acceptable to assume all geodesic motion happens in a flat plane. Finally, for the phi geodesic equation, there are 4 connection coefficients with phi on top. But since theta derivatives are 0, this last term goes to 0. So we just have this for our phi geodesic equation. This is associated with another constant of motion, which is r squared times the derivative of phi. If we take the derivative of this, apply product rule to both r squared and the derivative of phi, then here we use power rule to get 2r times a chain rule term. This result is equivalent to our original phi geodesic equation. We just take this to equal 0 and divide by r squared. The formula r squared times the derivative of phi is actually the same formula as the Newtonian angular momentum L per unit mass, which we will denote as curly L. This is a conserved quantity associated with translations in the phi coordinate, which are basically rotations, so it makes sense that it's the angular momentum. So we found 2 constants of motion for our geodesics, but there's one more thing we need, which is an equation for the squared length of our tangent vector, which comes from the metric. Expanding the tangent vectors using multivariable chain rule, we get our standard metric formula for the squared length of a vector, which expands to 4 terms using our Schwarzschild metric. The theta derivative is 0, and plugging things in, this sine theta goes to 1. So we have a formula for the squared length of our geodesics tangent vectors. Notice that the derivative of ct also lives in our energy constant of motion. With some algebra, we can solve for the derivative of ct. The derivative of phi can also be solved for using our angular momentum constant of motion. We can now plug these in to get this. As a final step, we can set the squared length of our tangent vector equal to a number epsilon. This number is 0 for light-like geodesics, and positive for time-like geodesics that massive bodies follow. We can then rewrite 1 minus rs over r as r minus rs all over r, and do some canceling and bring epsilon to the right-hand side. Then we can multiply all terms by r minus rs over r, leading to cancellations here and here. And we can again rewrite this as 1 minus rs over r. If we bring curly E to the other side of the equation and distribute, we find we get an equation that kind of looks like a total energy equation, involving a derivative of r for the kinetic energy and an effective potential term that only depends on r. And remember, the epsilon equals 0 case is for light, and the epsilon greater than 0 case is for massive bodies. Let's start with the massive body case. We can sub in the full formula for the Schwarzschild radius and use proper time tau as the path parameter. This means that epsilon is just the 4 velocity dotted with itself, which is the speed of light squared. Putting this all in, we can cancel c squared and then multiply all terms by 1/2. With a little more algebra, we can make this look more like the equation describing Newtonian orbits. We can replace curly L with angular momentum over mass, and replace curly E with energy over mass, then multiply both sides of the equation by mass, then move this constant 1/2 mc squared to the other side of the equation. If we now compare the equations for Newtonian orbits and orbits in general relativity, we see that both equations have a constant term on the left-hand side that's related to energy. The general relativity energy term looks more complicated, but the important thing is that it's constant. We also have an R derivative term that's like kinetic energy, and several terms that depend on R, which are like the effective potential. The Newtonian and general relativity effective potentials are the exact same, except for a term involving 1 over r cubed. This last term goes to 0 very quickly when r is large, but it can have a very large effect for small r. So the main differences between massive body orbits in Newtonian gravity and general relativity should only occur at small values of r, due to this new 1 over r cubed potential term. One way to understand these equations is to graph the effective potentials in each case. To simplify graphing the Newtonian potential, I'm going to assume all the masses and physical constants are equal to 1. We can then plot this function for different values of angular momentum L to get a sense of their basic shapes. Now let's focus on the L equals 0.5 case. We know that the total energy is constant, and the kinetic term and potential term can each get bigger or smaller, as long as their sum is a constant value. If we say this is the amount of total energy E in the system, we know that the orbiting body is going to be restricted to this region of the graph. The amount of potential energy can go up and down, but it can never exceed the amount of total energy. So a body with this amount of energy can't leave this potential well. The points where the constant energy line intersect the potential curve are the points where the total energy and potential energy are equal, meaning the kinetic energy must be 0. So the orbiting body will go back and forth in this potential well. This represents an elliptical orbit, where the radius reaches a maximum point, then turns around, then reaches a minimum point, then turns around again, with the radial velocity being 0 at the turning points. If instead the total energy line is exactly at the bottom of the potential well, then the potential energy and total energy are equal for all time. This means that the r dot term is 0 for all time, so the radius is constant for all time. This corresponds to a circular orbit with a constant radius. If the energy is very high, above the potential well, then the mass has too much energy to be caught in an orbit. So it just approaches the central mass, then leaves again and goes off to infinity, getting deflected by some angle. We can solve for the exact radius of circular orbits by setting the radius to be constant, so that the derivative of r, or r dot, is 0. This means that the constant total energy equals the effective potential energy, so V effective is constant, meaning its derivative is 0. If we take this derivative using power rule, cancel minus signs, multiply by r cubed, and cancel, we can solve for the radius of circular orbits in Newtonian gravity, L squared over m squared g big M. Now let's use this same graphing approach for the potential in general relativity. I'm going to replace the energy term on the left-hand side of the equation with curly E tilde to save space. Again, setting the masses and physical constants to 1, these are the potential curves for various values of curly L. We can see that there is a circular orbit right at this peak here, if we have the exact right amount of energy. But if we nudge this mass even a little, it will either fall towards the central mass or go off towards infinity. So this is an unstable circular orbit, because even a slight change to the energy will stop the body from orbiting altogether. Now, it's difficult to see on this graph, but there's actually a second circular orbit at this point here. This part of the potential graph actually forms a very shallow well, where circular and elliptical orbits can exist, just like in Newtonian gravity. So unlike Newtonian gravity, general relativity predicts 2 possible circular orbits for a given angular momentum. We can solve for the radii of these 2 circular orbits, assuming the orbit radius is constant, meaning the effective potential energy is constant and has 0 derivative. We use power rule on the rest of the terms, canceling these negatives and these 2's. Multiplying by r to the 4th, and canceling, we get an equation that's quadratic in r, and can be solved using the quadratic formula. Subbing in, we get this solution for the 2 circular orbits, given by the plus and minus signs here. These give the locations of the 2 possible circular orbits in general relativity. The circular orbit closer to the mass is unstable, and changing the energy even a little will cause the body to stop orbiting. The second circular orbit that's farther away is a stable circular orbit. Changing the body's energy by a little bit will simply change the circular orbit into an elliptical orbit. Also, we can compare the circular orbits from general relativity to the circular orbit in Newtonian gravity. If we take the speed of light to approach infinity, this term goes to 0. After canceling and replacing script L with L over mass, we recover the expected circular orbit from Newtonian gravity. So this means that when we're dealing with small masses and slow speeds, Newtonian gravity is a very good approximation for general relativity. Now, as we tweak the script L constant of motion, there is a threshold where the unstable and stable circular orbits become the same. Mathematically, this is when the discriminant of the quadratic formula becomes 0. We can solve this point to be when curly L squared equals 12 gm over c all squared. Plugging this back in for curly L squared, and knowing the discriminant is 0, we get a critical radius of 6 masses times a physical constant, which is also equal to 3 Schwarzschild radii. This is the smallest possible stable orbit in general relativity. This distance is also called the innermost stable circular orbit, or ISCO. Now, if we want to look at the orbits for light, we can just take our original equation and set epsilon equal to 0, which reduces the effective potential to just 2 terms. We can again find circular orbits by forcing the r-coordinate to be constant, meaning the effective potential is constant, meaning its derivative is 0. We take this derivative using power rule, cancel negative signs, multiply the equation by r to the 4, and cancel. And we can solve for a circular orbit at 3/2 times the Schwarzschild radius, which is also 3 times the central mass M times a physical constant. This means that, for a Schwarzschild black hole, if we turn on a flashlight sideways at exactly 1.5 times the radius of the event horizon, the light beam would orbit the black hole in a circular orbit. Because of this, the sphere with a radius of 1.5 Schwarzschild radii is called the photon sphere. If we graph the potential for the orbits of light, we can see the circular orbits appearing at 1.5 times the Schwarzschild radius for all values of curly L. But even outside this radius, the central mass will still impact the path of light beams, deflecting them somewhat from a straight path. The first evidence that light beams from distant stars were bending due to the sun's gravity was collected during a total solar eclipse on May 29, 1919, during the Eddington experiment, which was an early experimental confirmation of the predictions of general relativity. The last thing I'll cover in this video is another early experimental confirmation of general relativity, which is the perihelion shift of planetary orbits, specifically in the case of Mercury. Newtonian gravity tells us that planets orbit the sun in elliptical orbits, where the perihelion is the smallest distance between the planet and the sun. In general relativity, the extra 1/r³ potential term causes the perihelion to advance in the direction of orbit, resulting in a flower-like orbit shape. However, this effect is extremely tiny, and is usually only noticeable for small values of r over long periods of time. Perihelion advance in general relativity technically happens to all the planets in the solar system, but the effect is most obvious for Mercury since it's the closest to the sun. To derive perihelion shift, the goal is to get the formula for the planet's orbit radius r in terms of the orbit angle phi. The mathematical derivation of this is a bit crazy, so I'm going to speed through it, and you can pause if you want to go through it more carefully. We start with our energy equation, then use the case for massive bodies. We can use single variable chain rule to rewrite dr by d tau as dr by d phi times d phi by d tau, which we can rewrite using our curly L constant of motion. Then we multiply by r squared over curly L squared, and change variables so that r equals 1/u. This has the advantage of the derivative of r over r equaling the negative derivative of u over u. Then we multiply by u squared. We then differentiate both sides by phi and cancel du by d phi on all terms, multiply by this, and cancel the 2's. We can again change variables to w to absorb this constant, and we end up with this differential equation where alpha is this constant. On its own, the left-hand side of this differential equation equaling 0 is just the simple harmonic oscillator, with a sinusoidal solution. If we include the constant 1 on the right-hand side, we get the equation for an ellipse, where this e value is the ellipse's eccentricity. The last term is the correction from general relativity, and corresponds to the 1/r³ term from the effective potential. We can write w as a power series in alpha. Subbing in, if we set the terms without alpha coefficients equal to each other, we get the original Newtonian differential equation for w0, which we know the solution to. If we set the terms with the first power of alpha equal to each other, we get this differential equation for w1. If we assume alpha is small, we can ignore the alpha squared and higher order terms. So the orbit solution is basically the Newtonian solution w0 plus a small perturbation involving w1. After squaring this and using trig identities to replace cosine squared with a double angle, this differential equation can be solved by assuming a solution of this form, with this constant and sinusoids multiplied by linear terms, with 4 unknowns. If we find the second derivative and add it to the original function, we get this. Matching this form with the original differential equation, we get that small a is the eccentricity, small b is 0, big B is negative 1/6 e squared, and big A's value doesn't matter, so we'll just take it to be 0. Putting w0 and w1 back into the power series, we notice this sine term multiplied by a linear factor, and this is the term that causes the advance of the perihelion. So we have an equation for w. Using the small angle approximation for sine and cosine, we can rewrite this using an angle difference trig identity, and see that this cosine term does not have a period of 2 pi. Instead, it has a period of 2 pi over 1 minus alpha. If we multiply this by 1 plus alpha over 1 plus alpha, and assume alpha squared goes to 0 since alpha is small, we find that, for a planet to complete one orbit and get back to the starting radius, it must cover an angle of 2 pi plus an advance of 2 pi times alpha, which is the advance of the perihelion. To calculate alpha for Mercury, we can easily get the Sun's Schwarzschild radius Rs from the Sun's mass. To get Mercury's angular momentum per unit mass, curly L, we can make the simplifying assumption that the angular momentum is the exact same as when Mercury has a perfectly elliptical orbit. Comparing the ellipse equation to the W0 formula we derived and setting the numerators equal to each other, we can calculate Mercury's curly L in terms of its orbit eccentricity E and the semi-major axis A, which gives this. Putting all this together, we get a perihelion advance of 2 pi times 8 times 10 to the negative 8 radians per orbit. Knowing Mercury's orbital period around the Sun to be 88 Earth days, we can calculate Mercury's perihelion advance in 1 Earth century, which is 0.0002085 radians, or 43 arcseconds. In reality, Mercury's perihelion shift per century is larger, due to the gravity of the other planets in the solar system. But 43 arcseconds is the amount of observed perihelion shift that cannot be explained by the gravity of the other planets. It's a small correction factor that general relativity was able to predict. So to summarize this video, we used the connection coefficients for the Schwarzschild metric to calculate the geodesic equations for the Schwarzschild metric, for a constant value of theta equals pi over 2. The time and phi geodesic equations both gave us a constant of motion, and these let us turn the equation for the squared magnitude of a tangent vector into an equation that relates total energy, the derivative of the r coordinate, and an effective potential that depends on r. The main difference between Newtonian gravity and general relativity is this 1 over r cubed potential term. This term is negligible at large values of r, but causes non-Newtonian effects for small values of r, such as the existence of an extracircular orbit, a minimum innermost circular orbit, and the perihelion shift of elliptical orbits. General relativity also predicts that light rays will bend in the presence of mass, and can even orbit the mass along the photon sphere at a radius of 1.5 Schwarzschild radii. In the 108D video, we'll cover alternative coordinate systems for Schwarzschild geometry that will help make interpreting the geometry easier. In this video, we're going to...
Okay, so I think it's gonna make more videos in the future on this playlist. And I think after a certain point here, I kind of lost myself in the mathematics. So I think what my plan is gonna be is first I'm gonna research these topics here and try to get a better understanding of what I'm trying to become better at, because eventually I want to translate all these things into computation and build a library so I can work with things and test theories and stuff. So I'm gonna research these topics here. Then I'm gonna start this playlist and try to
Alright, welcome
code
to this
along
video series
the
on...
playlist. And after I'm done with both this playlist and the other one, I'm gonna go back to the videos on that special relativity one and try to see if I understand the mathematics better the next time. I'm not gonna go back from the beginning because I think the beginning I was following, but roughly the beginning, I think. So yeah, that's it for now. I'm not sure if I'm gonna come back later today or maybe tomorrow or some other time. But yeah, I'm gonna go eat something. So I'll be back sometime. See ya.